Okay, so this is where we ended up from last time. Um, we took the square root of both sides, and we ended up with 2e over m under the square root, and plus or minus v over here. So we come up with this problem. So in order to get a negative, I have a whole bunch of problems, right? And Glenn was right. Glenn was talking to me about, he was saying that it's impossible. And yes, it is impossible in this configuration for a bunch of reasons. Okay, so in order for v to show up as a negative number, if I have a fraction over here, it would have to be a negative in some way. It would have to be a negative in some way. So there would have to be, if I didn't have, let's say that there wasn't, just for a minute, forget that this radical is here, and there's just some fraction. If there's just some fraction over here and it's going to be positive, well, that would mean that both of these are positive. That makes sense. The energy is a positive number and the mass is a positive number, and the velocity comes out to be a positive number. That's what all makes sense in our world. And that is in fact what we see. All right, now forgetting the radical here for a minute, in order for v to be negative, either the energy would have to be negative or the mass would have to be negative. So to find out that the velocity, that v is negative, if this, without the radical here, if this was a fraction, I would either have to have negative energy or negative mass. Wow, that's kind of exciting. It's kind of exciting. But there's a bunch of reasons why this particular version of that, we don't have to, that's not going to be the case. Okay? It's not going to end out being the case. For one reason, and this introduces a new concept using our first three rules, a concept that's probably new to most of you. I think there might be only one student who might have seen this, and that is for anything under here to turn out to be negative, whether it's E or M, for the answer under the radical to turn out to be negative, that means that we have to have some value. This is, we're going to use our don't look down skills. Whatever this fraction is, whatever that fraction is, the green thing here, I didn't mean to color the whole thing. Whatever this green blob is equal to, it has to be a negative number, right? So what we would be doing is we would be taking square root of something, some squiggle, that is negative. All right. But that would mean, if we can take the square root of things, when we take the square root of things, we're finding what times what is equal to a negative. And it has to be the same thing times itself. Something times itself that would be equal to a negative. Well, the simplest case would be to ask, what is the square root of a negative 1? We know the square root of 1 because we know what times what is equal to 1. Well, 1 times 1 is equal to 1. If I take the square root of that, it's just 1. The square root of 1 is 1. Great. But what times itself would equal a negative 1? This problem gave math such a hard time that people, not engineers, not Euler didn't like this. People, they wanted to use this negative under a radical sign, but they couldn't make it work with math. They gave it its own symbol, which was I, and it means imaginary number. It stands for imaginary number. The square root of a negative 1 is I. So this is what the answer means, and it's an imaginary number. Okay, so yes, it is impossible in this particular formulation to come up with that unless I have some imaginary numbers going on here. We're going to run into imaginary numbers at the end of this course. We're going to run into having to take the square root of something in our very next unit in order to kind of figure out if we have the right function for waves. And this imaginary number is going to come back. Now, the reason why Euler didn't want to call it imaginary was because we find that we have to use this square root of a -1 just all kinds of places. In theoretical math, in engineering, you can't build buildings, you can't do physics, you can't do, there's a lot of chemistry, you need the square root of a -1. So we call it an imaginary number, but it's very real. It's very out there. Just kind of hard to wrap our minds around what exactly the mathy part of this is. Okay, so but I said you were thinking like Dirac, and you were thinking like Dirac, and I don't want to, I wasn't tricking you. So Dirac wasn't, he was looking at an equation that was similar to this one, but it wasn't quite this one. So in my looking at what equation he was actually trying to find the square root of, it was something more along this formulation. And wow, this looks very, very mathy, right? This looks very mathy. This is our don't look down skills taken to already starting out of the gate. But let's take a look at this. Now, this little guy, I'm going to tell you, we're going to come up against him later. So I'm going to put the stuff for later. I'm going to put the stuff for later in a gray. And he's just a little guy squared. We know how to square things. And he's just in a fraction. This is just a fraction. This is mass. I'm going to put a little green if you already know it. This is mass squared. You know how to square a mass. That's just a number. It's just a number of how many kilograms something is. C is the speed of light. And that's just the speed of light squared over there. So we know that. And this is a fraction. We know how to do a fraction. Okay. This little guy we are going to do in our third unit, and we're going to find really cool stuff, and it's just squared of that, which is a little bit different when you're doing that, guys. So I'm going to put it over all of it. This has to do with force fields, field lines of force. It's really, really fun. These two guys, so this is the change in bunch of stuff. Divided by the change, or the change in a bunch of stuff for every change in time. And instead of squaring that, we're really talking about the change of the change and the change of the change there. And we're going to do that, something very close to that, almost immediately in our Robbie homework for week 5 and 6. So this is gray, but it's about to turn into a green. All right, now this is just c squared. This is just the speed of light squared. So we got that, right? 1, you know about 1. All right. Negative, we got that. We got this whole thing covered. All right. Now this b thing is going to be an angle. And if you're doing MathPath, we will do this angle in our very next unit. Unit 2 for the MathPath. We will cover this guy. So we're going to cover this guy in Robbie right before we leave the very next Robbie, 5 and 6, before we leave motion for our MathPath. And then this guy will come next. This guy will be in Unit 3. And this guy, he's going to wait till the very end, but I will tell you that he's just hiding a bunch of stuff that we use all the time. It's particular ratios that we use all the time, and they're just kind of hidden in there. All right, so that was what Dirac was looking at. A simpler way of talking about what Dirac was looking at, and this is how the 60 symbols people talk about it, was he was trying to find the square root of this equation. So this is a relationship. It turns out that E is equal to mc squared is not the full thing of Einstein. Even Einstein's E is equal to mc squared Sorry, a little glitch there. He needed a little correction for momentum. That's what this P is. So the full equation is E. This is the same E as E is equal to mc squared. This is E squared. You also square the m and the c. So that's m squared c to the fourth, which is c squared squared. And then you have to add in this momentum correction. So this is what he was finding the square root of, and he decided to stick to the rule, his algebra rule, that when I take the square root of something, I have to get a plus and minus answer. And he said, what if that's really real? And that provided an explanation for, it predicted the positron. The positron is an antimatter particle of the electron. And here we have, this is a Wilson chamber, and this is a lead plate, and you can see that there are two different particles that are being traced across this plate. This plate has a positive charge on it, and so it attracts the plate is attracting this electron and is deflecting this electron. So I guess the positive must be somehow going through here. So the positive charge is deflecting one, it's attracting the other, and that was how we confirmed what Dirac's, following his simple rules of Algebra 1, was able to predict with his math. So that is thinking like Dirac. You're going to need it in the next wave unit when we get our wave function, and then it's just going to be cool to see how it predicted other particles when we get to antimatter later in the year. All right, bye.